In this video, I'll show you an example of a two-sided hypothesis test. So this is in the book 6.2 on page 408, and it's a scale in or out of calibration. So you have a little scale, you put a mass on top of it. In this case, it's 1,000 grams that you know it's a known quantity of weight, and then the scale gives you a reading. If the scale reads 1,000 grams, you know it's in calibration, it's calibrated. If it read something like 1,010 grams, then it's not calibrated properly. Similarly, if it read something like 980 grams, then it's not calibrated. So in this case, the one-sided test we're making is H0. The null hypothesis is that mu is equal to, the mean weight is equal to 1,000 grams. That means the alternative hypothesis is that mu is not equal to 1,000 grams. So it's either larger or smaller. It's just far away from 1,000 grams. So suppose that we weigh this same weight 60 times. So we're gathering data based on the same scale. That is, we're placing the same weight on the same scale and getting different observations. So this can actually happen. I mean, it'll just be small or large, but for the sake of computing, let's say that the sample standard deviation is equal to 2 grams. So there is some small variance. And suppose that we see an actual value of x bar, that is the average of all our data, is equal to 1,000.6. So we can use this to construct a hypothesis test. So if this were a one-sided test, we would just compute the area in the right side of the tail based on the distribution of x bar, assuming that it should be equal to 1,000. That's what we do for a one-sided test. But this is a two-sided test. We're checking for strict equality here. So to do the two-sided test, we say if the data is more extreme than a certain number, that is farther away from 1,000. So we're actually looking at the lower values too. So we have to consider this area too. Like if it were way over on the left-hand side, that would mean it's out of calibration also. So to compute the p-value, we're looking at the probability that the number is as extreme as this number, 1,000.6. So as extreme, it could be as extreme in the other way. So that's the difference between 1,000.6 is just 0.6. So we can go to the left. We went to the right here, 0.6. So we can also go to the left, 0.6. And that leaves us with 1,000 minus 0.6, which is equal to 999.4. So over here, the point we're interested in is 999.4. So we need to take the area both on the right here and on the left. because they're symmetric, we only need to compute one of them, and we can just multiply it by 2 because it's all symmetric about the mean 1,000. So again, you can use the same two techniques that I showed you in the previous video, but what we're using is x bar is distributed as under the null hypothesis, that is under h naught, the null hypothesis. X bar is distributed as normal with mean 1,000, standard deviation of, or variance rather, of 2 squared over 60. Okay, so then we need to find, we want to compute 2 times the probability that x bar is less than or equal to 999.4, and this is the CDF, the cumulative distribution function. So in R we can do this as, we can write this computation as 2 times P norm (999.4) mean is equal to 1,000. Standard deviation is equal to 2 over square root of 60, because R wants the standard deviation, not the variance. So this is equal, and this is equal to 0.0201, and this is the p-value. So this is a small p-value, which means that it provides evidence that the scale is not in calibration. If it were not a small p-value, then because of the way that we've set this up, we wouldn't be able to conclude that it is in calibration. The only thing we can say is that we didn't find any evidence that it was not calibrated, which is a different kind of statement. But that's how statistics works. So people commonly misinterpret this, and I'll have more about that in the next section. Anyway, it does not say that the scale is calibrated, as I've concluded over here. So we're not really, a more precise statement is to say there's no evidence that it's not calibrated.